I am Elgie Hale. I'm 88 and a half years old, and I am making this movie to leave with my posterity and my future posterity to inform them of my work on the Space Shuttle program. After the Space Shuttle began to fly again, there were 109 flights before the Space Shuttle was discontinued. On each of these flights, there were 6 of my joint heater protection systems. That 6 times 109 means there were 654 joint heater protection systems flown on the shuttle, and there were no failures. However, there was a glitch on flight number 2. On that flight, the primary heater burned in 2. I was able to direct the engineers in the control room at Cape Kennedy to switch from the primary heater to the secondary heater. The secondary heater provided heat, and the flight went off without a hitch. I made a video of this failure and explaining what had happened and sent it to NASA headquarters. I have also included this video in the movie that you see. I included one other video, which was a training video I made for the workers at Cape Kennedy to properly install a joint heater protection system there. I've included both of these movies in the movie I have made. If it doesn't sound like, it's my voice that you hear on the movie. If it doesn't quite sound like me, it's because that was 30 years ago, and I was much younger and much stronger then. I have been asked if I received financial reward for my work on the Space Shuttle. The answer is no, I received no special financial award. I was hired as an engineer. My title was Senior Design Engineer, and that was all the pay that I received. There were patents that were created, and these patents were in the name of the company, owned by the company, with my name as the engineer. NASA did present me with this Group Achievement Award plaque with my name on it for my work on the Space Shuttle booster. As mentioned later in the movie, they also flew my signature in space and returned my signature to me. I'm grateful to Dick Kinmont and my daughter Catherine Petty for their contribution to this movie. Dick Kinmont was our technical advisor, and he actually made the movie, piecing together many pre-recorded segments to make it what it is. Kathy was my means of transportation until I married Ruth Hess. She drove from her home in Sandy to Brigham City, where we worked on the text, and then frequently drove from my home in Brigham City to Syracuse to coordinate with Dick Kinmont. Kathy made a beautiful quilt for me. You see the backside of that quilt behind me. We've used it as a backdrop for this recording. When we turn it over, we see a beautiful space shuttle in flight and the astronauts in their various activities. I am so grateful to Kathy for this quilt and for the assistance she has given me in making this movie. One of the first payloads that the shuttle took into space after it began to fly again was the Hubble telescope, which gives us beautiful pictures and sees deep into space, farther than man has ever seen before. I have not worked alone on the problems that I've encountered in my life and in my career. The most difficult problems that I have encountered are as a father and as a design engineer. When difficult problems occurred, I have pondered deeply and prayed. And as I have pondered and prayed, inspiration has come into my mind, telling me of the solutions that I should follow. I am very grateful for this inspiration. On January 22nd, 1986, a great national tragedy occurred when the Space Shuttle Challenger was destroyed and all of the crew was killed in a huge explosion as it was being launched. The final assignment of my career as a space shuttle design engineer was to modify the solid rockets so that they could be launched at colder temperatures and a disaster such as this would never occur again. After the disaster, it was 2.5 years before the space shuttle flew again. This is the story of my contribution to the National Space Program. On the day of the disaster, I was at work at Thiokol, west of Brigham City. On hearing of the explosion, I went to the Thiokol control room and for an hour or more observed and re-observed the disaster on the monitors. I was concerned that the rocket motors made by Thiokol had been responsible. There's also a concern seen on the faces of all the engineers. The secretary were crying. I was concerned about my future employment with Thiokol. Several days after the disaster, I was called into the Thiokol management offices and asked to design a change to the solid-state rockets that would prevent this disaster from ever happening again. My first step was to build a 40-foot long heater that would be bonded on the rocket case over the O-rings. This change was called the Joint Heater Protection System. I sent the specifications for the heater out for bid, and about 30 companies responded. I was able to eliminate 10 of these companies, and then a Thiokol purchasing agent and I visited the other 20. We gave the contract to Long Beach, California firm owned by Chuck Sorensen. He shipped the first heaters, and I began testing them. This is one of the 40-foot long heaters that I designed to keep the O-rings warm, but it had to be tested. So I cut a short section of a rocket case, mounted the heater to it, and sent it to NASA test labs in Huntsville, Alabama for test. They had a huge fan that blew cold air on it, and the test showed that it did not produce enough heat. I could not increase the heat of the heat output of the heater. It was powered by 440 volts, and the 440 volts could not be increased. The best solution I could find was to bond cork on the outside of the case over the heater and the O-rings to keep the heat on the O-rings. This is a piece of the cork. It came in 20-foot lengths and was bonded to the outside of the case. The next problem that had to be solved was keeping the O-rings dry. As the system sits on a launch pad for sometimes several days waiting to be launched, it rains, the water runs down the outside of the case, and we had to do something to keep the water from running down into the O-rings. So I developed this piece of moisture seal. It is ribbed areas here. It goes 40 foot long, goes around the case this way, and this ribbed area keeps the water from running down through here and onto the O-rings. The straps are placed, the straps to hold it tightly against the case go in these grooves. I made a movie to teach the workmen at Cape Kennedy how to put the moisture seal on. I'm not going to show this movie. You'll notice as it starts that you can see the copper band of the heater. It's already attached to the motor, and it shows how to attach the moisture seal and the cork.
At this point, we have the heater installed on the motor. The ground straps have been bonded to the motor, and we're in the process here of cleaning the surface under, which will be underneath the moisture seal, so that it seals as it goes down. We're now putting the moisture seal in place. You see the right section of toward the center of the moisture seal. That's the sticky back tape that adheres to the pin retainer band that will hold it in place until the Kevlar straps are attached to it. Here you see the heater underneath the one surface of the moisture seal as it's being installed. At this point, we're cleaning the moisture seal. We're removing the talc and all impurities that might have been placed on it while it was being installed. It's very important this surface is cleaned so that the adhesive bonds well to it as the cork is bonded over the moisture seal. The bands you see to the side of the moisture seal are girth gauges, which will be only on the first 6 flight motors. You can see here the ribs that the Kevlar bands ride in. Here the Kevlar band is being placed in position, and just prior to tightening the Kevlar bands, the polysulfide sealant is placed at the hat band take-up, at the position of the hat band take-up mechanisms. That's at 30 degrees, 150 degrees, and 270 degrees, since this the take-up mechanism possibly could lift the moisture seal off the case at this point. Also, the polysulfide is placed at any point where we have instrumentation wires passing underneath the moisture seal to provide a ramp so that it will seal there, and also at the egress of the heater power leads. The Kevlar straps must be applied within 3 hours after the application of the polysulfide sealant, so that the sealant is soft enough to provide the proper ramps and sealing. Here we have the Kevlar strap take-up mechanism being attached to the Kevlar straps in preparation for the tightening. The mechanism that you see here is the mechanism that will be provided to KSC for installation of the straps on the first motor. However, you do not see the load cell here that will be provided with the straps, or the readout for the load cell. The straps are tightened to 1,600 pounds max. If they are not close enough to place the retaining clip in position, we then let it set for a few minutes, and then we tighten again. This may occur 2 or 3 times to stretch the straps far enough to install the retaining pins. Here we see the adhesive being applied to the area that will be covered by the cork. It's very important that the adhesive be applied to all surfaces, that all surfaces be wetted, so that we have a good seal to the motor, good bonding surface to the motor. The cork was dry fitted, the case was marked, and they will not only apply the adhesive to the moisture seal, to the Kevlar straps as you see here, but they will apply it to the case also at the edges of the moisture seal, those edges which will be covered by the cork. You can see the vacuum putty to the left and to the right of the area they're applying the adhesive. The vacuum putty is placed down so that vacuum bagging can rapidly begin after the cork has been placed in position. This EA934NA adhesive has a pot life of approximately 40 minutes, and as the adhesive is applied, a cure cup will be prepared, and this cure cup will be monitored to determine the state of the adhesive, to determine various steps later on. Here's a piece of cork that's had the adhesive applied. It's ready to be applied to the motor. After all of the surfaces have been wetted, we pour an additional cup of adhesive to the center of the cork so that there's sufficient adhesive to fill all of the voids. And as the cork is applied, we must have extrusion of the adhesive from both surfaces of the cork, from all along both surfaces of the cork. If we do not have that, we need to remove the cork and apply additional adhesive. As you can see, the cork is held in place with tape. Prior to applying the vacuum bag, this works very well. There's no problem with doing this. Here you see the wedge-shaped piece of cork being applied to the aft end of the field joint. Because of the unevenness of the case, it may be necessary to place spacers between this cork and the larger piece of cork. You can see a little spacer right there below the tape, and right here you can see another spacer being applied. If the case under certain conditions is not irregular, these spacers will not be necessary. Here you see the vacuum bag being applied. The cork that is being vacuum bagged will not go 360 degrees around the motor at one vacuum bagging. There isn't enough time to apply that much cork, but the vacuum bag goes 360 degrees. The vacuum bag is placed in position, and along the edges it's pressed into the vacuum putty. Now, since the area at the center of the vacuum bag is raised, there will be ripples in the vacuum bag along the edges, and pieces of vacuum putty need to be pressed into these ripples so that the edges can seal. After all edges of the vacuum bag have been pressed into the vacuum putty, the vacuum is applied, and then again the edges are pressed to stop all of the leaks that might occur.
After this first rocket motor was assembled with all of the joint heater protection parts, it was tested in a static test at the Morton Thiokol test facility west of Brigham City. The test results were then evaluated to make sure that all of the specifications had been met.
Activate head-end CO2.
Head-end CO2 pin puller activated.
Activate quench tool command forward and aft CO2.
Quench tool command forward and aft CO2 activated.
I will now explain how the rocket motor is assembled at Cape Kennedy. The rocket motor is 136 feet long. This is too long to be shipped by any means from Utah to the Cape Kennedy, and so the rocket motor is actually built in 4 pieces, and it goes to, and each of the 4 pieces are shipped separately to Cape Kennedy. And this is how it is assembled. The bottom segment arrives and is attached to the launch platform. This represents the launch platform, and it's securely fastened using explosive bolts around the perimeter. When it launches, those explosive bolts explode, leaving the rocket free to rise up into the heavens. The second segment then arrives, and it is placed on top of the first segment. And this is where the O-rings, the heater, the moisture seal, and the cork are. They're 40 feet long all the way around it. And this cannot be made at Cape Kennedy. It cannot be made at Thiokol, excuse me. It must be made at Cape Kennedy. And then the third segment arrives, goes on top. The next segment arrives, and now we have a 126-foot long rocket motor. The second rocket motor is assembled the same way. The bottom segment is attached to the launch platform. Beside the other rocket, which is now assembled. And then the other segments are assembled until we now have 2 complete assembled rocket motors side by side. I want to show you what the field joint of the rocket motor looks like. This is just a thin slice out of the upper rocket motor. This is a slice out of the lower rocket segment, and they fit together like this. Now there are 3 grooves that go all the way around the motor. There's an O-ring in each groove. This is an actual piece of an O-ring, and there's one here, and one here. And this is what seals the motor, that holds the hot gases in so they won't have an explosion. And when this was in the actual disaster, this was so cold that it couldn't move fast enough to fill the gap when it started to vibrate and let the hot gases through. And then after it's put together, a steel pin is placed in here. It locks it together, and it cannot come apart until the pin is removed. Each month, NASA held a design review meeting where the chief NASA engineers and the astronauts who would be flying the space shuttle attended, and there I presented to them the progress, first my design, and explained how it worked, and they had to approve my design. And then at the later meetings, I explained the progress that I had made in acquiring the parts and so on. As one of these meetings was approaching, I was very ill, and I went to the doctor's office, and Ruth and I were waiting to be called into the examination room, and I gave her a letter, an important letter, to run down to the post office and mail while we were waiting. And while she was gone, they called me into the examination room. The doctor checked me out and found how ill I was, and he placed me in a wheelchair, put an oxygen cylinder in my lap and an oxygen mask on my face, and wheeled me out of the Brigham Medical Clinic onto the street, and was wheeling me down the center of the street to the hospital. Ruth came around the corner, and she'll never forget the sight that she saw. At the hospital, they put me in an oxygen tent and started treating me for acute bronchitis. My supervisor came in with Thiacol to see if I was really ill again, but I was ill enough that he knew I could not attend the meeting, and so he canceled the meeting until I was well enough to go attend the meeting. The design review meetings were held by NASA so that I could make a report of, first of all, of my design, tell them of my design, tell them how it worked, and get approval to proceed with the design. One of the requirements of the design was that everything had a backup or a redundancy. In the heater, I had one heater strip, but there were 2 heaters in there, and the computer would switch from one heater to the other if the one failed. I had double heat temperature sensors, and the moisture seal, it had redundancy in that Kevlar straps were put around to hold it tight against the motor. But when it came to the cork, I could not figure a way to put something over the cork to hold it on. Anything I put over it became non-redundant. And so I could not figure out a way to do that. We discussed this for a while, and then the astronauts went to a corner of the room and held a discussion of their own. They came back in a few moments and said, "We will accept the risk of that. We can't figure it out either." After the shuttle began to fly again, on the second flight, I had a failure of the primary heater on one of the joints. I was at the control center in Thiacol, and they radioed me and talked to me about it, explained the problem. the heater had just failed. I directed them to have the computer switch from that heater that had failed to the redundant heater, which they did. And the flight went off without a hitch, and then I was able to evaluate the heater and find out what had gone wrong with it. But on each flight, after the fuel has all been expended in the rocket motors, they are released from the space shuttle and parachuted down into the ocean. A ship picks them up and brings them back into the examination room at Cape Kennedy. I flew down and examined the heater, and I'd like to show you the video that I made and sent to NASA headquarters showing them what had happened. I examined the heater, took the heater off and examined the heater back at Thiokol and had special work done on the heater. It was determined that there were foreign materials in the heater at that point. And so I rewrote the specifications for greater control of the atmosphere and of the heater components. And after this was implemented, this never happened again.
This is STS 29, the aft field joint, and we have here the cable connector, the heater connector of the primary heater. You can see that we've had a short inside the back shell of the connector. Approximately 1/2 inch of the arc of the connector has been burned away. This is one of the conductors of the cable that's burned completely free. We still have shield intact and good continuity between the shield and the shell. We have evidence of heating on the and burning of the insulation of the wire. Back here, you see we have good cable, no evidence of the white, normal color of the cable, no evidence of burning back there. We have evidence of overheating of the external insulation that was applied over the connector. This is the secondary connector. Electrical tests show that the secondary heater is still intact. It performed well during the pre-launch heat phase, and the primary heater had opened up, and this is the point obviously at which it had opened, requiring that power be applied to the redundant circuit to heat the joint. Out here of the wire, or the back of the connector, the wire that was broken, I think you can see it move there, but that wire is totally burned in two. There's no connection between that end of the wire and the pin inside of the connector.
On the third flight of the space shuttle after the disaster, I made arrangements to be in the control room in the NASA control room at Cape Kennedy, and made arrangements to bring Ruth and her brother Don and his wife Pat to see a launch. I left them out on the beach and went into the control room for the launch. It went perfectly. There was no problem with this launch. And to see a launch is almost a spiritual experience. You get a lump in your throat and your heart beats. It's really a sight to see. Following the launch, we took a trip up the East Coast, visiting the Civil War memorial sites. We went to Washington, D.C., New York, and then we traveled on to the church's historical sites in New York and in Nauvoo. One day at the Sealers room in the Ogden Temple, I told one of the Sealers this experience, and he dubbed it the day you broke the space shuttle. But what happened was as we were putting it together, the first shuttle together at Cape Kennedy, I put together the first rocket, and then the second rocket, and then they brought in that huge orange fuel tank and attached it to the two rockets. And it was just, they're so huge. You can't imagine how huge they are and how exciting it was to see that. And then they brought in the space shuttle and attached it to the rockets and the external fuel tank. And the day after it was brought in, I went up to look at the space shuttle, real close to it. And security was so tight on the space shuttle that no single individual could be alone in the vicinity of the space shuttle. Two people had to be together to make sure that nothing happened. And I was with a NASA engineer this day. We walked up to the top platform, and there I stood outside the windows of the space shuttle, looking in at the cockpits where the astronauts sat and their instrument panels. And then we worked our way down the space shuttle until we got to the bottom of it, and we were by the aft wing of the space shuttle at this point. And they bond heat insulating tile to the space shuttle. And then after bonding tile to all of the surface that will be heated by the re-entry, they spray a solution on it. I don't know what the solution is, but they spray it heavily on it, heavy enough that it drips off, and it forms small icicles on the aft end of the wing. And as we looked at that, I said to the engineer, it looks like they put too much of that solution on. I reached over with this finger, my right index finger, and I broke off one of those little icicles. Never thought a thing about it until I came to work the next morning. And as I entered the building, I was met by 4 uniformed NASA security guards. They walked up to me and said, someone touched the space shuttle last night. We think it was someone from Utah. I wished I could have died. And I said, oh. And the first thing I said, well, what happens if someone touches the space shuttle? And they said, the last person that touched the space shuttle got 6 weeks off without pay. And then I was speechless. I couldn't think of a thing to say. I just stood there looking at 4 security guards and then look at me. And it seemed like it was an hour, but after a while they left and walked over to the corner of the room, and they held a little meeting over there, and then they left. And I never heard anything more about breaking the space shuttle. Some incidental fun things happened as a result of my work on the space shuttle. I happened to be at the plant in Pasadena in Long Beach, California, which was building the heaters on Halloween, and they had their company Halloween party. And Chuck Sorensen, the owner of the company, was there with the best Halloween costume I've ever seen. You look at it and it looks like a little old lady is holding him in her arms, and she is actually dummy legs that he's walking with his own legs. And it's the funniest costume I've ever seen. Another incidental thing that happened as a result of my work on the space shuttle, I had been in meetings with Chuck Sorensen, the owner of the company that made the heaters, and after a couple of meetings he took me aside and said, Elgie, you need a hearing aid. He says, I have a friend down in Palm Springs, California that provides the hearing aids for President Reagan. I'd like to send you down and let him provide you with hearing aids. So after work that day, I got my rental car and I drove down to Palm Springs to the home of this hearing aid specialist, and he had a audio studio in his home. He took me to the studio, examined my hearing, and about 2 weeks later, sure enough, here came two of the best hearing aids I've ever used in the mail. I put them on, and man, could I hear well with them. I've never had a hearing aid that I hear any better with. And the only problem was that the whole hearing aid was down in the ear canal. And about every month, you had to take the hearing aids out and send them back to the company to get the wax out of the hearing aids. This was so expensive that I couldn't afford to use them. At the time of the Space Shuttle disaster, I was working on the Peacekeeper missile. I had the engineering responsibility for the safe and arm device. The safe and arm device is one of the key parts of any armament missile. There are two cables to the safe and arm device. One is the cable that provides the fire signal to the missile, and the other is the cable that provides control to the safe and arm device. The safe and arm device places a dead short across the fire cable so that no signal on the firing cable can fire the missile. And it removes that short and allows the fire signal to go through at the time that we want to launch the missile. The Peacekeeper missile is one of the most terrible weapons that's ever been developed on the Earth. It has 10 or more warheads and can be programmed to be fired in the United States, fly across to Russia, and knock out 10 or more Russian cities or 10 or more military bases in Russia. It's that powerful. And because of the power of that, the Russians have never been able to catch up with us in the arms race. Because of this and the strong economy of the United States, it was possible for President Reagan to go to the Berlin Wall and say,
Mr. Gorbachev, tear down this wall.
Because of my work on the Space Shuttle, on the Field Joint Protection System, I was invited along with some of the astronauts and some of the key people on the program to place my signature on this poster. This poster has flown in space with the Space Shuttle and returned to the Earth and returned to me. I feel honored to have been privileged to make the contribution I did to the America Shuttle space program, and very, very lucky.